All right, today we're going to pull back the curtain on artificial intelligence. We're going to trace the entire life cycle of an AI model, from just an idea on a whiteboard all the way to a tool that's actually out there in the real world. So let's just dive right in. AI doesn't just poof appear out of nowhere. It's engineered, it's constructed, it's deployed through this really fascinating and, yeah, pretty complex process. So, what does that journey from a simple concept to a powerful tool actually look like? That's what we're here to figure out. We're going to break this whole thing down into 5 key stages. First up, we'll talk about the architectural blueprint. Then, we'll move on to the assembly line, where it all gets built. After that, we'll peek inside the toolkit that engineers are actually using. Then we'll investigate the ghost in the machine, and we'll wrap it all up with the final inspection. So just like any big construction project, AI starts with a blueprint. It has to. And that very first step is choosing the right model architecture for the job you want to do. This one decision, right at the beginning, it defines everything, the capabilities, the limitations, and yeah, ultimately, whether the whole thing is going to be a success. First up, you've got regression models. Think of these as the foundational blueprints. They're pretty straightforward. They are perfect when you need to predict a specific number, like what's the price of this house going to be based on its size, or how many widgets are we going to sell next quarter. They're really good at finding that clear mathematical line right through your data. Next, we've got recurrent neural networks, or RNNs for short. Now, their special trick is this internal loop, which lets them process information in a sequence. It helps them remember what came right before the thing they're looking at now. This makes them pretty good for basic language stuff or analyzing stock market data. But here's the catch. That memory can be really short-term. I mean, they can literally forget the beginning of a long sentence by the time they get to the end. And that limitation is what pushed us towards more advanced design. Now, for anything visual, you're probably going to be using a convolutional neural network, or a CNN. This is the blueprint for computer vision. CNNs use these special tools called filters that kind of slide across an image, automatically learning to spot important features, like the sharp edge of a table, the texture of a carpet, or even something as specific as a cat's ear. And that brings us to the current state of the art, transformers. Now, unlike those RNNs that read things step by step, transformers look at the entire sentence or the whole dataset all at once. They use this incredibly powerful mechanism called self-attention to figure out how important every single word is in relation to all the other words, no matter how far apart they are. This right here, this is the magic behind today's most powerful large language models. So if you look at this table, you can see the evolution laid out pretty clearly. The early RNNs, they really struggled with long sequences because of this problem called vanished ingredients. Basically, they just forget the stuff from the beginning. So LSTMs and GRUs came along with these special memory gates to fix that. But the real game changer? The transformer. By just ditching that one-by-one sequential process, it can handle everything at once. And that high parallelism, that's what makes it so incredibly fast and powerful for the massive data sets we have today. Okay, to make this a little more real, let's zoom in on that CNN filter for a second. Imagine you have a tiny little magnifying glass, that's our filter, and it's looking for one specific pattern, like say a horizontal line. It just slides across the image, section by section, and does a quick little calculation. And whenever it finds a match, boom, it lights up that spot on a brand new map, which we call a feature map. By layering thousands of these maps, each looking for a different feature, the network eventually learns to see the whole picture. So, you've picked your blueprint, awesome. But now you need a factory to actually build the thing. In the world of AI, we call this the assembly line, a structured, repeatable pipeline that turns that theoretical model into a system that actually works. And what's really important to get here is that this isn't just some loose idea someone came up with. No, this is a standardized process. It's been formalized by the International Telecommunication Union. It all starts at the source, where you identify the raw data. Then a collector gathers it all up, a preprocessor cleans and formats it, which is an absolutely critical step, and then it gets fed to the model for training. Finally, a distributor sends the model's predictions to the sink, which is the end application where a decision is actually made. This whole systematic flow is just crucial for building AI systems you can rely on. But, that clean diagram, it doesn't really capture the messy reality of what it takes to build one of these things. In the real world, engineers have to pick specific tools for every single step. And let me tell you, they have some strong and often conflicting opinions about which ones are best. And this just perfectly illustrates that reality. I mean, forget the textbook theory for a second. On forums like Reddit, you see the raw, unfiltered feedback. Here's a developer being incredibly blunt about their experience with a vector database, which is a special kind of database for AI called Pinecone. They're citing latency and reliability problems, and they're praising a competitor, Qdrant. This is the real talk. And it is not an isolated case. Here's another one, a user talking about their AI app, switching from a tool called Chroma to one called Fize for better performance. So the key takeaway here is that in the real world, picking a tool isn't about finding the one best option. It's about navigating this really complex landscape of trade-offs in performance, in stability, and of course, in cost. That there's a problem that no tool, no matter how good it is, can fix on its own. It's this emergent property of these complex systems. People often call it the ghost in the machine. These unintended patterns and skews from our own world that get encoded right into the data, and as a result, get learned by the algorithms themselves. Let me show you a really well-documented and pretty stark case study of this. So the Compass algorithm was designed to predict how likely a defendant was to reoffend. On the left, you have a Black woman with one minor prior offense who was rated as high risk. She didn't reoffend. On the right, a white man with a more serious prior offense was rated low risk. He went on to reoffend. This shows how a model, just by learning from historical data, can produce outputs that are just completely skewed or totally counterintuitive. So where does this stuff even come from? Well, from an engineering point of view, these skews can creep in at a whole bunch of different stages. You've got historical bias, which just means the model learns from data that reflects our own past societal imbalances. You've got representation bias. That happens if, say, your training data for a facial recognition system is mostly people from one demographic. And measurement bias can happen just by deciding to measure the wrong thing, like using arrest records as a stand-in for actual crime rates. Okay, this all brings us to our final, and maybe our most critical stage, the final inspection. Knowing that these systemic risks are out there, how can we build a better quality control process? How can we catch and fix these things before a model gets deployed out into the world? Well, one really compelling idea is to start treating AI development a lot more like we treat pharmaceutical trials. It's a powerful analogy when you think about it. Phase 1 is all about basic safety testing in a closed virtual lab. Phase 2 is testing for effectiveness, but in a more open yet still secure environment. Phase 3 would involve a full impact assessment. And then, crucially, Phase 4, continuous monitoring after deployment to watch for any unintended side effects. It's basically a roadmap for building safety and reliability right into the process itself. And this leaves us with a massive question for the entire industry. When a system that we've built from the blueprint all the way to deployment produces these skewed and harmful outcomes, who's responsible? Where in that whole life cycle do we build in accountability? Is it the person who provided the data? The developer who built the model? The company that deploys it? It's a challenge the field is grappling with right now.